Well, over the years, I've grown to love the material in this lecture very much. I'm going to run it by you very, very quickly. I apologize about that. But it's better that you see it quickly than you don't see it at all. So here, take a look. Convergence tests for series. The first one, I suspect most of you could just prove this by yourselves, but I'm going to run it by you for the sake of completeness. The comparison test. Let A be the sum of I equal 1 to infinity of A sub n, and B equal the sum of 1 to infinity of B sub n, be series of positive numbers where A sub n is less than or equal to B sub n for all n. If B converges, then so does A, and in that case, the value of B is greater than or equal to the value of A. Okay. Start off with let A sub n, capital A sub n, and capital B sub n be sequences of partial sums of the series A and B respectively. Okay, so note that A sub n is A1 plus A2 through A sub n, and since A sub I is less than B sub I on a term-by-term basis, this is less than the partial sum of Bn. And since these are positive sums, okay, the value of the series B is equal to the least upper bound of the set of B's. Okay, so B is greater than or equal to the partial sums of A. So it is an upper bound of the set of partial sums of A. The set of partial sums of A is increasing, bounded above, therefore it converges to its least upper bound. Simple. Okay. Okay, now let's go to something that's not quite as simple, but will allow us to just really leverage a lot of our knowledge. And the limit comparison test. Okay. Again, let's let A and B be series of positive numbers using the usual notation. And suppose that AN over BN, okay, their terms, has a limit, okay, as n goes to infinity. If L is greater than 0, then A and B have the same convergence properties as each other. Okay. So let's take a look here. The proof, suppose that L is positive. Since this limit exists, there is a number n, so that for capital N for little n greater than capital N, we will have the ratio of AN to BN minus L in absolute value to be less than L over 2. Okay, which is to say for large values of little n, the ratio of AN over BN is between negative L over 2 and 3L over 2. We do a little arithmetic here. Okay. So in particular, okay, I can say that AN is greater than or equal to L over 2 times BN, and AN is less than or equal to 3L over 2 times BN. Okay. Given that information, we're set. Suppose that A converges, then its tail, the sum from n equals capital N to infinity of AN converges. By the comparison test, we see then that the sum of n equal capital N to infinity of L over 2 times Bn converges. Since L over 2 is not 0, it will then follow that the sum of n equals capital N to infinity of Bn converges, and that is equal to 2 over L times this series. Therefore, since its tail end converges, B must converge. Now suppose A diverges, then A's tail diverges, and so by the comparison test, it follows that that the sum from n equals capital N to infinity of 3L over 2 times Bn diverges, as the tail of Bn is equal to 2 over 3L times the series n equal capital N to infinity of 3L over 2 times B. Okay, it follows that B converges, the B diverges. Okay, so the series converge or diverge together. We can now go on to, I think this might be everybody's favorite series test, the ratio test. Suppose that A is a series of positive terms, and take the limit of n plus 1 over A, and say that limit exists and it's equal to R. If R is less than 1, then A converges. If R is greater than 1, then A diverges. And if R is equal to 1, we just don't know. Okay. Proof for R less than 1. Let rho be a real number such that R is less than rho is less than 1. So we slip in a number between R and 1. From the existence of the limit of an plus 1 over an, it follows there is a capital N such that for little n beyond n, we have that an plus 1 over an minus r in absolute values is less than rho minus r. Okay? Rho minus r is going to be a positive number. All right. So we do our usual bit getting rid of the absolute value sign so we can do some arithmetic. At the end of this, we can say that for n bigger than capital N, A sub n plus 1 over an is less than rho. Therefore, A sub n plus 1 is less than rho times A sub n. And we can play this again. We can say an plus 2 is less than rho times an plus 1 is less than rho squared times an, and so on, doing this, that A sub n plus k is less than rho to the k times an. All right, now we can apply the comparison test to see that the tail end of the A series is then is less than the tail end of the series rho to the n, should be a capital N minus k, right? Capital N, well, rho to the n minus k. Actually, it's just n minus k times an. The latter series is a convergent geometric series because n here is a constant. As a consequence, the series an converges. Okay. Part 2, where r is greater than 1, will follow similarly. We end our test with the integral test, okay, which is powerful. We can prove things about series with it. We can prove things about integrals with it. Suppose that f from the closed interval, from the interval 1 to infinity into r, is a decreasing function such that f of x is positive for every x greater than 1, and that f is Riemann integrable on the interval from 1 to n for every integer n greater than or equal to 2. Okay, now let a sub n be equal to f of n for all n element of the natural numbers. Then 1, the sum from k equal 2 to n plus 1 of ak is less than or equal to the integral from 1 to n of f of x dx is less than or equal to the sum from k equal 1 to n of ak. Therefore, okay, the integral from 1 to infinity of f of x dx, which we haven't actually defined yet, and the integral from, and the sum from k equal 1 to infinity of ak either converge or diverge together. Let's prove this. Let a(n) be a sequence of partial sums for the sum of k equal 1 to infinity of ak. For an integer n greater than or equal to 2, consider the integral from 1 to n of f of x dx. Let p be a special partition, okay, be with the integral values 1, 2, 3, 4, up to n plus 1, with each point of partition a consecutive integer. Then, okay, u sub p of f is equal to, okay, what it is, right? We use the definition. In this case, x sub I, as it were, is I plus 1, and x sub I minus 1 is I. The difference between them is 1, and so my upper integral is just the partial sum an, okay? and because we can say that m sub I is equal to f of I because f is a decreasing function. Similarly, we can get that L sub p to f is equal to the sum I equal 2 to n plus 1 of ai, again using the same partition, just by working through the definition of that particular partition. And so we say that an plus 1 minus an is equal to I equal 2 to n plus 1 of ai, which is less than or equal to f of x dx, which is less than or equal to my partial sum an. And from this we see that number 1 is true. Again, we get number 1 just by using definition of upper and lower sums and that particular partition P. Okay, so since f of x is greater than 0, it follows that the integral from 1 to 2n of f of x dx increases as n increases. Okay, therefore the integral from 1 to infinity, which we're tacitly defining to be the limit of this integral as n goes to infinity, is the least upper bound of this sequence. So an minus 1 is less than or equal to minus a1 is less than or equal to this sum, okay, this integral. And so an plus 1 is equal to an plus, or less than or equal to an plus this integral. It follows that the sequence an is bounded above as this sequence of partial sums is increasing. It follows, therefore, the corresponding infinite series must converge. Okay, now contrast this with, suppose that this integral from 1 to infinity of f of x does not converge. That is to say that the sequence of integrals from 1 to n of f of x is not bounded above as n increases. Therefore, as integral from 1 to n of f of x is less than or equal to an for all x, it follows that the sequence a of an of partial sums must increase without bound as well. Therefore, my sum from n equal 1 to infinity of a n diverges.